I would like to thank you guys for joining us, Professor Tong, Professor Holloway, Professor Lee, and Professor Gill, and also Professor Sulaiman. I thank Professor Sulaiman and Professor Al-Garhi for inviting us for this meeting. It's been a pleasure. We're going to talk about monitoring air quality using remote sensing data, what kind of social aspects for that, what are the efforts in the world regarding this particular matter, why it's important, the history of monitoring air quality using remote sensing, and other topics. The order we're going to go through is we're going to start with Dr. Tracy Holloway from University of Wisconsin-Madison. Dr. Holloway is the Gaylord Nelson Distinguished Professor at the University of Wisconsin-Madison. And she's been a faculty of Wisconsin Medicine since 2003. And she serves as the team leader for the NASA Health and Air Quality Applied Science Team, short for the acronym for HAQAST. The acronym is HAQAST, and led efforts to promote the Energy Analysis and Policy graduate certificate program in the Nelson Institute. She has many awards, involved in many meetings, and invited to many talks. She's a great person. I met her in person. She's wonderful. And I also would like to welcome Dr. Shuwei Lee. He's going to help me in moderating this. This is the first time I moderate a panel, so he's going to guide me through this panel here. Thank you, Dr. Lee. Dr. Lee is the Sarah Schallenberg Brown Professor of Meteorology at Yale University. He concerns teaching and research concerns in the interaction between the terrestrial biosphere, the atmosphere, and anthropogenic drivers. He has a lot of very important published articles in many prestigious and well-known journals like Nature and Science, and I'm very glad for him to be here. And when we go to the other panelists, Dr. Tong and Dr. Gill, I'll introduce them once we reach their turn. So as I said, we're going to start with Dr. Holloway to talk about HAQAST and the community part of this topic. Then we're going to move to Dr. Tom Gill, who's going to walk us through a history of using remote sensing in air quality data and how the remote sensing progress over time. And then we will enjoy Dr. Tong speak presentation about the climate extreme events in using remote sensing data. Dr. Tracy, you have the floor. You may start, unless Dr. Shoei, do you want to say anything before we start?
No, I think.
Thank you, Tarek. Will we have questions all together at the end, or just should we reserve time? How would you like to do that?
Due to time limitations, I think we're going to do 15 minutes presentations, and then the questions, we're going to take the questions at the end of the whole session. Like when you all finish, we're going to start taking questions.
Great. And would you like me to share my screen, or do you want to share the slides?
If you can, that will be awesome. If you can share your screen.
Sure. Well, thank you so much, Tarek, and thank you to all for organizing this session. It's really a pleasure to be speaking today, and especially a pleasure since I know this is focused on students, and there's so many exciting career opportunities and implications of satellite data for air quality analysis. So, as Tarek said, I'm a professor at the University of Wisconsin-Madison, and I lead the team for NASA that's trying to make satellite data more relevant, useful, and impactful for public health and air quality. And this initiative is called the Health and Air Quality Applied Sciences Team. I'll refer to it as HAQAST. And actually, Daniel Tong, who you'll be hearing from in a few minutes, is also a member of HAQAST. I'm going to start out with this talk is not going to be very sciencey, but it's more about how science gets done and what is the purpose of science and how are questions formulated. And the traditional way for science to move forward is for the researcher to have an idea, kind of that aha moment, and to propose implementing that idea, maybe with with a proposal to the National Science Foundation or NASA. They hopefully get funding, and then they go ahead and do their work for 2 or 3 or 5 years, publish some papers, and then go on to the next project. And that's sort of the typical life cycle of research. And that works very, very well. And, I have no criticisms about the standard model of research, but it isn't the perfect model for everything. And air quality is a great example of a problem where it is changing very rapidly with immediate concerns from dust storms and volcanoes to energy system change, to policy relevance, to health impacts. And it's a field where it doesn't always work for an individual satellite scientist or data scientist to just be working on their own for 5 years and publishing in the academic literature. It's a field where there's so much going on in regulatory, public health, decision-making, and research across disciplines that there's a benefit to having rapid response activities, and also a benefit to collaboration, and a benefit to having kind of a focused effort rather than having a lot of different researchers doing their own thing. And that was really the motivation that led to the formation of the NASA HAQAST activity. And I'll tell you a little bit about that in a few minutes, but I'm going to start talking to you about, my own background a little bit so that you have an idea of the frame that I put on the NASA HAQAST approach to doing research. And for a long time, I have been very interested in thinking about how to make science more relevant to public policy. And I don't think it's a coincidence that, Dr. Tong on this grant, he has also got his PhD in a public policy school, if I'm not mistaken, Daniel, that we've all been looking at this problem of research from the lens of how to make it more useful to society and to the world. And in my own career, I've really benefited from a lot of support to grow, not just as a scientist, but also as an engaged scholar. And back in 2011, I participated in a program called the Earth Leadership Program that was really focused on helping scientists make an impact. And the word impact can mean something different. It may mean making your science exciting to kids. It may mean helping to shape policy on climate change. But whatever it is, it's this idea that we can do a lot as scientists by stepping outside of our traditional approach to science. A few years later, I was part of a new initiative through the American Association for the Advancement of Science called the Leshner Leadership Institute, which similarly was trying to push scientists to do science a little bit differently. And one of the main things I remember from the training in Washington, D.C. Through the Leshner program was an emphasis on two-way communication. This idea that science communication doesn't just mean doing your science and telling people about it. It means that you want to listen to the needs of your audience, whether those are professionals or other scientists and other disciplines or the public. This idea you need to listen and use the information that you're getting from these partners to shape the scientific process itself. And I'm fortunate to be here at Wisconsin, where there's a real commitment to public service, especially in my home institution of the Nelson Institute. And this same approach has also been propagated through my work with the Earth Science Women's Network that I helped found about 20 years ago and now is zooming along. And if you're not part of ESWN, you might check it out. So that brings us to HAQAST. And the mission of HAQAST is really to connect the billions of dollars of public investment by NASA in observing air quality and make it relevant to air quality and public health professionals. We say on our website, our mission is to bring the power of NASA science down to earth and deliver it into your hands. I often think of this as a bridge, where on one side you have all the research and science and power of NASA, and on the other side of the bridge, you have potential organizations that could benefit from this science. That includes the Environmental Protection Agency, the World Health Organization, these large public-facing organizations that could benefit from satellite data, but do not themselves have that as part of their mission. But actually, it's very wide, going down to individual cities and individual states, mayor's offices that may be interested in sustainability, nonprofits who are interested in health, and organizations around the world. And in fact, in many parts of the world, we don't have ground-based monitors for air pollution, so satellite data may have an especially high value. The history of this NASA effort goes back to 2011, when we formed the NASA Air Quality Applied Sciences team, and that was focused really just on air quality in the United States. In 2016, it was expanded to be health and air quality, and not just the United States, but also the globe. And that international focus and health and air quality connection continues in the current generation of the team, which runs through 2025. There are 14 members of the current HAQAST team. Each of these serves as the principal investigator of a grant where they proposed to NASA how they would like to build this bridge between science at NASA and practitioners. And when we think about this bridge, I describe it that way in part because so much of what we're doing is trying to come up with new ways of using satellite data. And sometimes these questions are easy to answer, but usually the new ways of using satellite data are difficult because they've never been done before. And that's really why it motivates a research approach, an applied research approach, where these are all leading researchers spanning Alaska to Florida, and many different types of institutions. Each one of these leaders is working with collaborators. So all total, we have about 70 or more co-investigators as part of HAQAST. And we operate with 3 different types of projects: the projects that the members proposed when they were selected for the team, what we call Tiger Team projects, where different subsets of this community work together on short-term, high-impact applied projects that were motivated by requests from these health and air quality organizations. And then finally, work that I'm working on with my team at the University of Wisconsin focused on communication. Because one of the things we found is that for us to be an effective bridge, people need to know that we're here, and there needs to be a lot of different ways that they can access the exciting science and resources that our team are developing. So I really like to always emphasize that this is not something that it's that easy to do just as a little side project in your free time. It really requires professionals and engagement. And I'm really honored to be working with Dr. Jenny Bratbert, who has her PhD in microbiology and a lot of background in science applications to policy. And then 2 students at the University of Wisconsin who are managing our website, editing videos, developing social media, and really doing our best to amplify the work of this team. We are building a wide range of different ways for users to plug in to our activities. They can do so, kind of passively by checking out our website or visiting us on social media. They can become a little bit more active by subscribing to our newsletter. They can come to our meetings. They can collaborate on projects. We ask them to review proposals. And we have recently launched this group of kind of what we sometimes call super users, or the HAQAST ambassadors, which are high-level representatives from organizations around the world who have been very active in using satellite data for air quality and health. And we treat them as really a sort of our brain trust of outside users, where we can get their opinion and hear from them what they see as priority topics. We have built meetings through in-person collaboration and ongoing activities for many years. And we have meetings almost every 6 months. These went online during the pandemic, but our meetings typically draw about 300 people per meeting, with a mix of online and in-person attendance. We had one just a week ago here in Madison, Wisconsin. If you're interested in getting involved, we would love to have you as part of this growing community. You can visit our website at HAQAST.org. If you'd like to play around with satellite data, we have this tools and resources where there are a lot of different links, and I would recommend starting with the Getting Started tab. If you'd like to know more about the work of our team, some of the examples of the kind of big picture projects we're working on are highlighted by our Tiger teams, covering environmental justice, building, enabling stakeholder access, NOx in cities, satellite data for the Air Now system, agricultural fires, and more. And it was really, an honor a couple of years ago when we were highlighted in a commentary on making open science work for science and society, and really highlighting NASA and this NASA HAQAST team as a good example of this push toward making science more open, accessible, and socially engaged. And so we have a couple papers that describe this team. We have a lot more at our website, and I look forward to answering questions during the Q&A. Thank you very much.
Awesome. Thank you, Dr. Holloway. That was a really wonderful presentation. We're gonna make the questions available after we all finish. Next, we will move to Dr. Tom Gill from UTEP. Dr. Tom Gill is an interdisciplinary Earth system and environmental scientist who has been at UTEP faculty member in geological science and the ASE PhD program since 2004. He has many awards in his records and many scholarly and creative activities, including participating in the Theater Perform Comedy in Geoscience in October 23rd, 2017, Geological Society of American annual meeting. And Dr. Gill, the floor is yours. You may start now if you like.
Thank you very much, Tarek, and thank you to the organizers, and great appreciation for inviting me and for being here with this great group of people. Today, I would like to illustrate where we've come from and where we're going to in terms of remote sensing of air quality through the lens of dust storms, which is my particular focus of research. I am located in El Paso, Texas, in the Chihuahuan Desert, in one of the dustiest parts of the Western Hemisphere. And so even though I know we have participants from all over the world, most of my illustrations and images will be from Southwest North America, but clearly where we've come and where we're going in remote sensing monitoring of air quality through the lens of dust storms can also be applied everywhere worldwide. So this is the first, you could say, high altitude, well, space, maybe not satellite, but space image of Earth. It's a little bit more than 76 years old. It was obtained from a rocket that had an old-fashioned film camera on it that was sent up over White Sands Missile Range in New Mexico, United States. And we'd look at an image like this now and we might laugh at it a bit, but it really tells us where we've been. And it was a very historic image from 76 years ago, looking down at Earth from space for the first time. I would like to argue that this is the first, or one of the first, remote sensing images of a dust storm. This was during the Dust Bowl in the United States in eastern Colorado in the year 1936, and an aircraft photograph of a dust storm getting underway on the high plains of eastern Colorado. And we can actually see a lot of things that we now understand about the dust generation and transport process from this image about 85 years old. We've been detecting dust storms through satellite remote sensing for more than 55 years, and we've come a very long way. On the left, we see here a cloud of dust moving off the West African coast into the Atlantic in June 1967 from the ESA-5 satellite. Really, this understanding and these early papers based on these early satellite images helped us understand the transport of African dust across the Atlantic towards the Caribbean. On the right, it is the first satellite image of a dust storm in North America from the first Landsat in January 1973, with some dust plumes barely visible on the right of this image over the Mojave Desert. The first geostationary operational satellite, GOES-1, was in operation more than 45 years ago. And very early on and very quickly, GOES satellite image from that first mission was used for understanding and tracking dust storms. Here we can see two very large clouds of dust over the central plains of the United States. And in the late 1970s, Kessler et al. Realized that these satellite images could tell us some things about where the dust is coming from. They noted, for example, that the dust boundary is fairly nicely coincident with the Texas-New Mexico state border. The western limit of the dust nearly coincides with the border. And since the border is a political division without geological significance, at first it's difficult to understand why it's so clearly associated with the boundary of dust. But then they looked at some other remote sensing imagery, and this was multispectral photography by the Apollo 9 astronauts in orbit of that same Texas-New Mexico border area. And they pointed out that the border is very well defined by land use and the difference in water management, with center pivot irrigation systems more on the Texas side and more rangeland on the New Mexico side. And they concluded that satellite eye views supported by a ground survey reconfirmed the well-known connection between dust storms and intensive cultivation of certain arid and semi-arid lands. Of course, now, 45 years after the first GOES satellites, we're up to GOES-17 and GOES-18, which provide a great tool for monitoring dust storms. Here we see some GOES loops of, again, a dust storm over West Texas and northern Mexico. GOES now provides images that are minutes apart and great for watching the evolution and progress and transport pathways of dust events, with the spatial resolution down to about 500 meters for these images only minutes apart. So we've learned a lot through that. Going back in time again, though, after the original GOES, a great revolution in understanding airborne dust from space came from a instrument aboard a satellite platform that was actually designed originally to monitor and made great strides in monitoring another aspect of air quality, which is ozone, the total ozone mapping spectrometer, which operated aboard the Nimbus 7 satellite from 1978 to 1994. It was designed for monitoring ozone, but it provided unprecedented data on sources and transport of dust. Basically, dust was a quantitative interference in the ozone signal. And as they say, one person's trash is another's treasure. And that interference actually allowed quantification of dust. And the long-term record from TOMS let us do some things such as basically discover and delineate what we now know as the global dust belt, extending from North Africa across the Arabian Peninsula and West Asia to China, as well as the intensity of dust emission from other portions of the globe. The TOMS sensor also demonstrated the significance of playas, which a geologist and geographer refer to a playa as a dry or ephemeral lake bed in a dry land, as well as ephemeral streams flowing into them in dry lands, and the role that they play as the globally most important sources of dust, from the Kalahari in southern Africa to Lake Eyre in Australia to the Atacama in South America and the deserts of North America. It was through the TOMS record that we really connected playas and dry lake beds to being the world's most potent dust sources. I'd say the most valuable player in the team of satellite sensing of dust has been NASA's MODIS. On board Terra since 1999 and Aqua since 2002, MODIS has been revolutionary in helping us detect dust source locations with spatial resolution to 250 meters and 2 images per day. With MODIS, we were able to identify individual dust point sources on the landscape and create inventories of these sources as related to land use, geography, and geomorphology. Using data on individual dust storm point sources derived from MODIS, coupled with geological maps, soil maps, land use maps, researchers developed the concept of preferential dust sources, which related dust storm intensity to landform type. This allows large areas of the Earth, such as the Taklamakan Desert of China, the Lake Eyre Basin of Australia, the Chihuahuan Desert of North America, to be mapped into their relative dust emission potential, high and low, or even gridded in terms of relative dust emissivity that gives the potential for using dust emissivity now as a satellite confirmed land use term that could be put into dust forecast models. MODIS also refined the record from TOMS in terms of the quantification of where the dust sources are coming from, where dust is persistent in the atmosphere over the Earth, and how much of the dust is associated with anthropogenic land use and ephemeral water bodies. However, the NASA EOS era, which includes Terra and Aqua, and thus MODIS, is coming to its end of life very soon. Perhaps by next year, these missions may end. So in the future, we'll have to rely on other satellite-based sensors to look for and understand dust storms and other aspects of air quality. The successor to MODIS is VIRS, which is up there now and gives very good data and will continue operating for a long time. But there are other new tools that have come in and are coming in, which I wanted to briefly mention. For example, fleets of small satellites from private Earth observation companies, such as PlanetScope from Planet Labs, which has basically what they call flocks of doves, fleets of small satellites flying across each other that can detect dust sources with high spatial resolution. For example, let's look at the dust storm of March 16th, 2021, in northern Mexico. This is a MODIS image. We will further zoom in on this part of it. Here on the left, we see MODIS with its highest spatial resolution, showing us very clearly the dust plumes emanating from this agricultural region with center pivot irrigation in the Chihuahuan Desert. But PlanetScope has a spatial resolution of down to about 4 meters. If the PlanetScope dove flock is in the right place at the right time, you can get incredible resolution on dust sources. For example, here, showing exactly the individual little plumes of dust coalescing out of this area of center pivots. And again, if it's in the right place at the right time, the multiple satellites in the dove flock give very good temporal resolution. For example, another dust storm in northern Mexico, again, an area of center pivot irrigation. We see at 10:06 in the morning, not too much going on, but literally 11 minutes later, when another one of those PlanetScope passes over, you can actually see where the dust storm has started and where within the center pivot field is emanating from. And there are some amazing new tools coming, some new missions that are just gone up or going up in the next year or two, such as EMIT, the Earth Surface Mineral Dust Source Investigation Mission. It will map the minerals on the Earth's surface in dust source regions using an imaging spectrometer aboard the International Space Station and provide great information about the composition of dust, which is very important from a climatic standpoint and understanding dust radiative forcing. If you're interested in EMIT, I do want to let you know that there will be another wonderful webinar coming up a week from today, actually, on November 9th at 3 p.m. USA Eastern Time, sponsored by the International Society for Aeolian Research with Dr. Greg Oken of UCLA, who is on the EMIT mission team. And to sign up for that EMIT webinar, go to aeolianresearch.com/seminar. Another wonderful tool that is coming up is PACE, the Plankton Aerosol Cloud and Ocean Ecosystem Mission, which will provide hyperspectral imaging and multi-angle observations of atmosphere, ocean, and land systems, and will provide a great amount of particulate matter and dust data through optical depth, dust speciation, and other data that will improve aerosol transport models for more accurate air quality and atmospheric management. And then finally, last but definitely not least, I'm very excited about TEMPO, the Tropospheric Emissions Monitoring of Pollution mission. It's scheduled to launch in early 23. It will be focused on North America, including Canada, Mexico, and the US, and will retrieve aerosol properties of 3 different aerosol types: carbonaceous, desert dust, and urban industrial particulates at very high spatial resolution across North America. And similar missions are planned for other parts of the world by various different space agencies. So I'm very excited about the future of remote sensing of air quality and dust from satellites. I do want to finish by saying there's not one magical sensor that will provide all of the answers for understanding dust storms or particulate matter from satellites. Each particular platform has its advantages and disadvantages, with a trade-off between spatial fidelity, temporal frequency, and data availability. But with all of the new platforms and sensors out there, I think there's a great opportunity for incredible new data and applications of air quality from satellite missions. We've come a long way since this first image of Earth from space 75 years ago, and remote sensing has been a valuable tool for tracking and understanding dust sources and other aspects of air quality and air pollution for over 55 years. And these new tools are definitely going to be opening up new doors in air quality sensing from space. Thank you very much for your time and attention. I really appreciate the opportunity to be with you today.
Thank you so much, Dr. Gill. That was very important. And now we're going to move to Dr. Daniel Tong. Dr. Daniel Tong is a research professor at Center for Spatial Science and Systems, a research unit affiliated with the College of Science at George Mason University. He's interested in improvements to the national air quality forecast capabilities. And Dr. Tong, the floor is yours. You can start now.
Thank you, Tarek. And hi, everyone. It's really an honor to be here to discuss our interest in the dust storms, wildfires, and its impact on society. I saw there's a question in the chat on this. Hopefully, we'll be able to answer some of those questions. So this on the left showing what has been going on in the past 50 years since we have the main air quality regulation rules. That's the Clean Air Act. Since the 1970s, our economy has been growing, except come to recently, the pandemic, you see, is coming down a little bit. And then also the vehicle miles traveled has increased. So it's a population, energy consumption. And then our CO2 emission has been capped, and now it's coming down. So it's the emissions of air pollutants. On the right, that's showing the PM10 air quality trend. So PM10 is the particles less than 10 micrometers in diameter. We have seen a similar decrease in trend until recently. We are seeing some spikes coming up. This is mostly caused in the region of northwestern US, as where we are seeing that actually the PM10 counting has been going above the dashing line, which is the national air quality standard. So why is that? Our hypothesis has been that emission control and technological advances has brought down the concentration of air pollutant like PM10. However, in recent years, climate sink in, and we are seeing that climate is playing a bigger role of that. So why PM10 is increasing in recent years? Where do air sources come from? This is a picture showing all kinds of emission sources that can contribute to the PM10 in the air, that including power plants, agricultural, industry, transportation, and animals, right? To feed an increase in population, we have increase in animal farming. Then we also have natural sources such as desert dust, biomass burning or fires, and also trees from the ocean, and occasionally we have volcanoes. So the last files considered a natural source, especially dust and biomass burning. So even the anthropogenic sources have been decreasing. We are seeing a rapid increase in the activities of wildfires and dust storms in the United States. On the left, showing the burned areas in the past 30, 40 years. And on the right is a collaborative work with Professor Gill. We look at the dust storms across the US. So pretty much of my time, the rest of the time, I will be focused on dust storms. From 1988 to the time we finish our study, we are seeing that the dust storm has been increasing about 12% per year, right? It's not molecularly changing. However, this increasing trend is very obvious. So even the air pollution has been decreasing, but we are seeing extreme cases such as a wildfire and a dust storm has been increasing. What causing those changes? Mostly is climate. We are looking at different kinds of climate indices, such as ENSO, which is El Nino Southern Oscillation, PDO, Pacific Decadal Oscillation, and the rest of those different kinds of climate index that you can be used to describe the change of the climate and also the ocean. We found that the PDO here is the most important one, has the stronger correlation for both long latitude dust and also high latitude dust. So what is a PDO? PDO, the Pacific Decadal Oscillation, showing the change of sea surface temperature over North Pacific Ocean. So we compare the 1990s and the decade of 20, we found that the surface temperature over North Pacific Ocean has increased significantly. At the same time, we are seeing that over the western coast of the United States, the ocean temperature actually has decreased. So this special pattern will change the flow of the atmosphere, will bring more air from the north to the United States compared to the air from the south. The air is colder and drier, so that means you will bring less rain to the United States. So next, let's look at the soil moisture to see if that's the case or not. So here showing the difference in the soil, the top layer soil moisture between the 2 decades. If it's red or warm color, that means it's getting drier. If it's blue, that's getting wetter. Pretty much over the western US, especially the southwestern United States, you are seeing predominantly a drying pattern of that. That's explain why we are seeing more dust storms, we are seeing more wildfires. Really, wildfire and dust storms are like the twin, produced by the same parents here, including climate change and also human activities. So what does that mean to our society? One unique thing about the dust in the American region is that a fungus coccidioides living in the soil. The fungus, once inhaled by human, can grow rapidly inside your body and also can flow with blood, get to your brain and grow out of some part of your body. It's really messy. So because the fungi live in the soil, we want to see what more dust storm bring more fungi to the cities and get people infected. So we put where we detect the dust storm into the map and then overlay that to where we report more valley fevers. We find that in the same state that you see a higher level of infection of valley fever, and you are also seeing more dust storms. We also zoom into 2 endemic regions, in that's Phoenix and Tucson in Arizona. We found that only the dust storm close to the cities actually have a bigger impact or stronger correlation. This is a work by Morgan Gorris. She predicts how valley fever will increase or change in the rest of the century. The bad news is this valley fever rate previously only confined to the southwestern US is going to spread very quickly and pretty much to the entire western US at the end of the century. Valley fever is not an only concern. Another big concern is highway safety. I wish you have never driven into a dust storm, but if you are, there's very little you can do. You can keep driving, hit other people, or you can stop and hit by others from behind. So there are many accidents caused by dust storm around the world. Yeah, other impacts I'm going to briefly cover later. So that's actually a myth in the United States. How many people were killed by dust storms? If you look at the official or all these sorts of public platforms, such as natural hazard statistics, there are very few deaths from dust storms. Actually, you look at the newspaper, for example, here we found that one report showing 6 people killed in a 25 vehicle pile-up. So that's inconsistent. We look at the 3 data sets, including the natural hazard statistics, and the storm event data is also a data set from NOAA, and then also the DOT police report, the fatality analysis report system. Surprisingly, we found that even the natural hazard statistics only got 1 to 5, but the actual number from the police reports is much higher. We have 13 to 33 deaths each year for the time period we studied. So that's because the natural hazard statistics was an incomplete reporting system, and sometimes they put the dust into high wind. But dust is different from high wind because soil particles are added to the air, and reduce the visibility, and also lower the traction at the surface. You need a longer distance to brake. So where do we see those fatal accidents? This is for the 11 years we studied. It's pretty much across the United States. It's not just in the desert regions. So for example, in Washington State, this is other farms that Professor Gill mentioned earlier. In Texas, those farms are active dust sources. They are not covered by vegetation. And also in the between Phoenix and Tucson, that's about 10 miles. That's very dangerous. They have hundreds of accidents just occurred in the 10 miles. And Lotusburg in New Mexico, we have some major accidents. Have 6 or 7 people killed in one accident. So we have come up a map showing the effects of dust storms on health and safety in the United States. And now we are working with United Nations to have a global map like this. We have the valley fever infection, animals, aviation safety, road safety, marine, and renewable energy reduction, because dust can cover the solar panel and reduce productivity. And harmful algal blooms. It can also have water contamination, food contamination, bring the microbes to the cities, bring the heavy metals to the household, and also sometimes bring radioactive contamination to the population. So I will wrap up here. Basically, my message is anthropogenic emissions decrease, yes, but extreme events are mostly driven by climate as increasing. It's going to have a huge impact on our health and our environment, and as well as the economy. I will end here. Thank you for your attention.
Thank you so much, Dr. Tong. And now we have 5 minutes for the question. Dr. Shui Li, we can raise 5 minutes of brief discussion about the topic, maybe answer one of the questions here, which is from Ubong: how can this tool be harnessed to monitor air pollution and hydrocarbon exploration and processing sites? Dr. Shui, the floor is yours.
Well, I'm not obviously in a position to answer the question. Maybe the question should be directed to the panelists, right? Maybe Tracy can take a stab at that question, perhaps.
Sure. With hydrocarbons from hydrofracturing sites, the hydrocarbon that satellites can see most clearly is formaldehyde. And formaldehyde can be directly emitted, but it's also chemically produced. So, a lot of users want to see VOCs, and unfortunately, satellites are limited in the VOC detection capability, with formaldehyde being the most powerful. I would say an indicator that has been more widely used for fracking has been NO2, because NO2 is a gas that is seen quite well by satellites, and there are multiple satellites up that detect NO2 on a daily basis, and Tempo will provide it on an hourly basis. And especially when you're away from other large sources, as fracking facilities often are, like in West Texas and parts of Colorado, or where they may be the only big source of emissions, these same sources that are also emitting VOCs, but the NO2 may be the one that's best, the satellite product that's best suited for evaluating their size and activity.
I also think remote sensing, Tracy, you may know specifically better. There are sensors that also do a great job at looking at hotspots of methane emissions too.
Yeah, absolutely. That's a real good point, Tom. And I think that the methane community is really exploding, and there's a lot of private companies like GHGSat that are detecting methane as well. So one of the interesting things about methane is that you have the government-owned satellites that are providing global coverage, like akin to particles and NO2, but you also have these deployable, constellations of satellites that can detect down to the facility scale for individual leaks, and that those are being hired by large energy companies to assess leakage at their own facility. So the methane story is actually very layered with different types of instruments in both the public and the private sector at different scales.
Characters, do you have time?
We have 3 minutes, yes.
Okay, maybe I will ask a slightly different question here, and I don't see any hands being raised. So my big concern about air quality monitoring, right, at least in the United States, is that a lot of the stations, ground stations, are biased towards more open space, green space, not really representative of dense neighborhoods and poor neighborhoods. So it may give a false impression that air quality is super good. In fact, in those neighborhoods, the air quality may not be as good as we would have hoped. I wonder if the data from satellite can help us identify the bias and perhaps help the EPA or other monitoring agencies to relocate and redistribute the monitoring stations to have more representation of the real air quality in cities.
Yeah, maybe I'll say a few words and then hand it off to Daniel, because you're 100% right. That's been a problem. And, monitors are so expensive that they've often been deliberately sited in areas that do represent more regional average or urban average concentrations. Satellite data, and I'd say especially NO2, because it is a local pollutant and it can indicate combustion from local sources, both industrial and transportation, can be used. And I think it's especially powerful when you're comparing the top-down estimates of what satellites are seeing with what we know is happening on the ground. And actually, Daniel has done some exciting work in that. Do you want to say?
Yeah, sure. This is absolutely very important, especially right now when we're concerning about the environment justice or injustice. The work we are doing right now is trying to use satellite data and combine it with high resolution model data to map out air pollution at different neighborhood level. That's actually it's going to provide some information to answer that question. And it also depends on which air pollutant you are talking about. Like NO, for example, NO2 is very short-lived, right? So if you just travel from highway to a residential area, you're going to see a very large gradients on that. So I think this is going to be a very important question for the community to address. And HAQAST is doing something on that. And I think there are other communities such as low-cost monitoring the sensors. They are also doing great work on that. Hopefully, in the future, we even have a higher resolution satellite to be able to answer that question.
I just quickly add, right? We have low-cost sensors monitoring particulate matter in New Haven, and the monitoring station here is no way representing the real PM level in the city. It's biased, always biased. So that's really a concern. Thank you for the answer. I think it's great.
Thank you so much, Dr. Tong, Dr. Shuwei, Dr. Tom Gill, Dr. Tracy, and the organizers, Dr. Sulaiman, Dr. Ben, and Dr. Al-Garhi. Thank you so much. I'm going to try to follow up with the questions asked in the QA. Maybe send it to Dr. Al-Garhi, send him the answers. So you'll send it to the people who asked it. Thank you so much. I hope the audience enjoyed it. I myself enjoyed it and learned a lot. Thank you so much, and have a great rest of your day. Bye.
Thank you so much for this discussion. Really enjoyable and very important to all of us.
Thank you, Dr. Sulaiman.